Welcome back. Now that we have the weighted graph in place, we can move on to That's not how you spell it. Nope. There we go. It's a dumb joke, but this is actually the 3 attempts it took me to get it right. I'm sorry to tarnish his legacy. I can never remember how to spell his name. But it's the bottom one here, D-I-J. Anyway, what we're going to do now is walk through the steps of how the algorithm works. We're going to visually go through it one step at a time before we translate it to code. And the graph we're going to work with looks like this. So it's a weighted graph. Here's, 6 vertices, and each edge has a number associated with it. Hopefully it's clear what goes with what. And the shortest path that we want to find is from A to E. So there's a couple of options, and this is a very small graph, and most of the ones in the real world are quite large. But even with this small data set, there are many ways to get from A to E. We can go around the edges, we can go through the middle. There's 4+ options. Not to mention, could take some absurd routes to get there, including loops. And anyway, so that's our goal. So here's the algorithm boiled down or distilled to 4 main steps. Each time through the main loop, we'll do something like this. So we look to visit a new node. That's the only way that this works is we start at A and we visit nodes. And there has to be some order that we visit them in. How do we decide where to go next? And we start by picking the node with the smallest known distance to visit first. So I'll come back to all of this visually in just a moment. But we always pick the node that has the smallest known distance from A, and we visit that first. Then once we move to that node, we look at each of its neighbors, and then for each one of its neighbors, we sum the distance from A to that neighbor. And if it's smaller than what we currently know about, if it's a smaller distance, then we update our file, essentially. This is a lot to talk about without showing you, so I have a bunch of diagrams like this we'll get to in just a moment. But those are the steps. So every time we visit a new node, every time we're looking sort of to start the loop over, we visit the smallest known distance from A in our case. We're looking for A to E. So we start with that, we move to that node, and we look at each of its neighbors. And for each neighbor, we already have a distance on file, how far it is from A. And we will update it if the new distance that we've summed together is less than what we currently know about. And I know that sounds crazy, so I'm going to come back to it. But here's our diagram. This is sort of the setup for the next 30-something, maybe 40 slides. I just fade between them, and you'll see stuff come and go. So the same graph is up here. We're going from A to E. It has the same values on there. And down here is sort of the file I was referring to, where we store the shortest distance from A for each vertex. So A is a special case because it's going to be 0. But something like B, well, eventually the shortest distance from A to B is 4, of course. But then like E, which we'll get to, that's our goal, is to figure out what the shortest distance is. And anyway, we'll be updating this as we go. And then previous, I'll explain in just a bit. So let's begin. And the very first thing we do is initialize the shortest distances from A for every vertex. And we don't really know how to do that. That's the whole point. We don't know what the shortest distance is from A to get to F. Imagine there's a million vertices on here. You can't just know from the beginning. So what do? We just put infinity in here. We put a large value, basically an unknown. We don't know any of these values except for one, which is A. We know the shortest distance from A to A is 0. From one vertex to itself, that's going to be 0. So that's what we start with. This is how we always initialize the setup. So we'll make a data structure for this. We won't talk about code just yet, but just imagine you're writing this down on a piece of paper. So A to A is 0. A to B right now is infinity. We don't know. A to E is infinity. So we ignore that. Now remember the steps. The next thing we do, every time we look to visit a new node, we pick the node with the smallest known distance to visit first. Well, we have one choice right now. A, that's the smallest. 0 is clearly smaller than infinity. So we start with A. So we pick the smallest, that's what that's showing here. And I've added it to the visited list here. Now what we need to do is look at each of its neighbors. So from A, we have 2 choices, A to B, A to C. And I'm always going to go alphabetically, it doesn't really matter. So we're going to start with A to B. So what we do is we go down to B, and we check, well, currently the shortest distance from A to B is infinity because we don't know any better. That's just the initial state. So what we found is that the distance from A to B right here is 4. So 4 is definitely less than infinity. So we update this to say, all right, the new shortest distance from A is 4. And you'll see that we update some of these a couple of times. Of course, we can see, looking at the graph, there's nothing shorter between A and B. It's definitely 4. That's the smallest we'll get. Okay, so we update that here. And then over here in this previous structure, we're going to update B and set it to be equal to A. So what that essentially does, and I know I'm missing quotes, it's not valid code, but what this does is it says the way we got to B was through A. And that's obvious in this situation, but later on, something like F, if we update the shortest distance to F, we want to remember, did we get there from D or did we get there from C? There's multiple options. So this structure helps us piece together where we came from, the node that happened or that occurred right before B on our path. So that's a simple one. So we've done everything we need to do for A to B. Now we look at A to C. Okay, so currently from A to C, we have infinity. So we look at that distance, the total is 2. So of course we're going to update this. 2 is definitely shorter. And then we come over here to C, and instead of null, we update it to say, all right, the way we got to C was from A. And that's it for A. We've done both neighbors for node A. So now what we have left to do is we repeat the process. We pick the smallest known value, the shortest distance from A that we haven't visited. So remember, we've been to A, so we're not going to pick A because we just continually do A over and over and over. But now we have two choices. B, the distance is 4, and C, the distance is 2. And when I say distance, it's the distance from node A. Okay, so as you can see, we start with C. That is the smallest known distance. So now we look at C and its neighbors. And there's 3 choices, but we've already done A to C, so we're not going to do that. So now we have C to D and C to F. All right, so let's look at C to D first. So what we do, again, is we look at what the current value is from A to D. It's stored at infinity. So we calculate the new value from A to D through C. And the way we do that is by summing A to C plus C to D. So, for example, we know that C to D is 2. Okay, so we take 2. And then we look at how did we get to C? What was the previous for C? And the previous is A. So then we figure out what is the distance from A to C? 2. So 2 plus 2 gives us 4, of course. And obviously it's easy for us to look at, but you have to think about what your code is going to be doing. So we sum those two together. That gives us 4, and we'll update this right here to say 4. That's definitely smaller than infinity. And then we also need to update over here to say how we got to D. And the way we got there was through C. So that's what we add. Okay, next up, we're going to look at C to F. Same process. So C to F is 4, and then A to C is 2. And the way we know it's definitely this edge is if we look at C, we stored A as the shortest way to get there. So 2 plus 4 gives us 6. So we come down to F, and we check, is 6 less than infinity? Yes. So we update it, so we store 6 here. And then what we need to do is update our previous. How did we get to F? Well, what came right before it was C. So hopefully you can see how this becomes useful. What we're storing here is the shortest path to any given node from A. So the shortest way to get to D is from C. And then the shortest way to get to C from A is directly from A. So we only need to store the previous shortest path. So it's sort of step by step how we get to each node, what's the shortest way to get there, and we combine them all to figure out how to get to E eventually, which isn't done. So we update it to say we came from C. Now we start over. We need to pick the smallest value, shortest distance from A that we haven't visited. So we've done A and C. So we can cross those off. And the shortest thing is either B with 4, D with 4, or F with 6. Well, definitely not 6. And I'm picking B first just because it comes first alphabetically, but either one would work. They're both 4. So now we look at B, and B is easy because we've already visited A to B, so that's not happening. But we have B to E. Okay, so we'll look at that. And that gives us 3 plus what came before B. How did we get to B? We came from A, so that edge is 4. So 3 plus 4 gives us 7 as the new total, and that's definitely less than infinity. So we update this to say, well, the current shortest way that we can get to E is 7 units, or whatever this is, 7 miles or something. And then the way we got there, over here, we'll update this to say we came from B, right? So if we stopped right now, it's not the shortest path, but we have a path that we could piece together. So we got to E from B, and we got to B from A. Now, out of the unvisited nodes, where do we go? So we've done A, B, C, and now we have D, E, and F. Well, which one is smallest? D. So we're going to D next. Okay, so here's D, and we have a couple of options. We've already been to C, so we're not going that way. So we either go to E or F. I'm going alphabetically, so E comes first. So we'll look at D to E. So that edge is 3. So now we calculate the total distance from A to E through D. So the total here is 7. And if we look at what we have stored for E right now, it's already at 7. So that doesn't win. It's not less. It's not shorter. So we're not going to update it. You could, if you wanted to, you could write your code so that you added 7 here if they're equal. But there's no reason. We already have a path that is 7 units long. This one. So we ignore it. Now we move on to the next, which is D to F. So our new total here to get to F is 5. And if we look at what we have stored right now, we have 6. Well, 5 is less than 6, so we update it to say 5. And we come over here to F, and we no longer come from C. That's what we had before. This was the shortest way to get to F. But now it's actually shorter if we come from D. So we update it. So this is saying, the fastest way to get to F is from D. The shortest path from A to D is through C. The shortest way from A to C is, through A, because there's a direct line from A to C. Okay, so that finishes up D. We did this edge, we did this edge. So now we cross it off, we visit it. There we go. Now we're going to pick the smallest again. So we have 2 options. We visited all these 4, A, B, C, and D. Now we have E and F. Which one is smallest? Which one has the closest distance or the shortest path to A? Right now, that's F. 5 is smaller than 7. So we'll start here. And we only have one option. We've already done this edge. We've done this edge. So now we look at F to E. So the distance is 1 to go from F to E. And what's the shortest path to get to F? So we add that all together, 4, 5, 6. And if we look at what we currently have stored for E, we have 7. We have 7 from this path on the outside, but we've now found something shorter. So we update this, and we cross those off, and now we add 6. And then, of course, we have to update how we got there, because right now we're storing the old version. If you look at E, we're saying the shortest path from A to E goes through B, but that's not the case. We now just found something shorter where we go through F. So we update this. If we look at E, there we go. We now say the shortest way to get there is through F. And just that one letter difference now makes a huge difference because it's a cascade, it's a chain. Because we look at where F, all right, well, to get to F, we went through D. To get to D, we went through C. To get through C, we went through A. And at this point, we have nowhere left to go aside from E. And that means that we're actually done. We found the shortest path. So to break that down again, I won't go step by step, but every time through, we pick the current smallest distance from A that we haven't visited. We explore each of its neighbors, and we calculate the new shortest distance to each neighbor. And if it's smaller than what we already stored, we update what we stored, and then we reflect the change over here in our previous data structure. And this allows us to piece everything together. So if we look at this, we're done now. All we have to do is work backwards. So to get to E from A, we start at E. And we look at, all right, F. Well, to get to F from A, the shortest possible way, that's what this is all storing, we end up with a list of the shortest way to get to any node from A. The shortest way to get to D from A is through C. And to get to C, we have to go from A. So A, C, D. That's the shortest way to get there. The shortest way to get to E is through F. And from F, first we go through D. From D, we go through C. C to A. So this is our shortest path. A, C, D, F, E. So Dijkstra's algorithm works not only to give you the shortest path between two nodes. At the end, the way we're implementing it, we'll have a data structure that gives us the shortest path from A to all the nodes. And that can be very useful. If you run this once and you don't change your graph, you have this structure that gives you the shortest path to go anywhere. You don't have to rerun it for every, if you're trying to go from A to B and then A to D and A to E, you run it one time and you get all that information. All right. So I know it's a lot. These slides took forever to make, and I hope they were helpful. I definitely recommend stepping through them on your own and just without me kind of explaining what I'm doing in the video, or even on a piece of paper. That's how I learned it originally, literally graph paper, drawing these charts out and keeping track of, all right, we bend to A, cross it off. We bend to B, cross it off, and drawing the graph out. Because from here, the jump to the code isn't that bad. It's just going to be difficult if you're not sure how this actually works. So I really, really, really recommend that you do that. If you're at all confused, if you don't feel like rewatching the video, I don't blame you. It's long. It's not that exciting to go through, but it can be a little more engaging if you do it on your own. And then once you understand it, jumping to the code is a lot easier. All right, so that's what we're going to do next. I'll actually show you sort of real pseudocode, if you will. And then if you want, you can try and implement it. Or, because this is a little complicated, totally understandable if you just code along with me. All right, it's coming up next.